Okay, thank you for the invitation. I wish I were actually in Marseille, but I'll take this as second best. And please, I don't mind, I don't know what the style is in this school, but I certainly don't mind being interrupted with questions. Okay, so scattering amplitudes of asymptotic particle states, certainly something we can consider in quantum gravity. And they're important physical observables, and they're associated to the boundary of a space-time. I'm going to be talking about asymptotically four-dimensional spacetimes rather than the bulk. And that's nice because it's very hard to formulate diffeomorphism invariant observables with bulk quantities. And it's possible, it's certainly true in quantum field theory and might also be true in quantum gravity, that they're in some sense a complete set of observables. Not that they're an answer to every question that you'd like to ask about asymptotically four-dimensional Minkowski space, but it might be that every question could, not that they're directly an answer, but that everything can be extracted from that. Once you know that, you've understood the theory. Okay, so, but we know far less about it, even at the classical level, than is commonly presumed. And I'd like to draw attention to three major unsolved problems for scattering in general relativity in asymptotically flat spacetimes. The first one is, how do we define it? Now, this is much more subtle than the problem that is usually, not exclusively, but the problem that has been most discussed by mathematicians. And that is, if you take an asymptotically flat, complete space-like slice, and you specify all the diffeomorphism, strictly diffeomorphism invariant data on that slice, and then you evolve it using the Einstein equation. That problem is well defined, but that is not the same as the scattering problem, because in the scattering problem, there are all sorts of subtle quantities, observables, or degrees of freedom, we could call them, that there are infinitely many, that are diffeomorphisms. They're not diffeomorphism invariant, but they're diffeomorphisms that go to something non-trivial at infinity, and therefore change the physics. So, for example, a boost is a diffeomorphism, but nobody would say electron at rest and an electron moving, that's the same thing. But in general relativity, it becomes much more subtle. A related problem to this is, what are the non-trivial symmetries and conservation laws? 50, 60 years ago in gravity, or in this, the things that are conserved by scattering. And 50, 60 years ago, people would have said, okay, yeah, we know the answer to that. It's the energy, the total momentum, total angular momentum. General relativity is a highly, and also the boost mass, the boost charge is a highly nonlinear theory. Nothing else is going to be conserved. Now we've understood, really only in the last 10 years, that there are in fact infinitely many more conservation laws, and we don't know what they all are. And this is a very central problem. This isn't something that we need, loop gravity or string theory, or, this is a problem, some basic question about the laws of physics that have been totally verified experimentally. In some approximation, you have classical physics, you have asymptotically flat spacetimes, and we don't know what the symmetries of that problem are and what the conservation laws are. And these conservation laws, these subtle conservation laws have observational signals. They make predictions for experiments. One is the most famous of these is the memory effect. But these have an infinite number of generalizations, and we don't know what all those are either. So what I'm going to do in this talk is review some, I'm not too sure exactly what the level of the school here is. And so, any sort of questions along the way would be welcome for that reason. I'm not sure exactly what level to present it at, but I'm going to review stuff that has happened in the last 5 or 10 years. And then it's always fun to talk about something new. So I'm at the end, I'm going to talk about some work we're excited about some progress on this question of the symmetries. And I've also written a book on the first half of the lecture, which you can get from Princeton University Press, came out a couple of years ago. And it's a big subject, a lot of people working on it. And I've had a lot of wonderful collaborators. I can't write them all out. So the starting point for the recent chain of developments that I'm going to discuss was the observation that there were 3 things that had been discussed within different communities in physics that were actually really exactly the same thing, not related, not almost the same thing, but exactly the same thing. And one of them was the study of asymptotic symmetries, which was pioneered by Arnaud Deser and Misner, and then Bondi, Vanderburg, Messner, and Sachs in the 60s, in which there were these infinitely many, they noticed that there had to be more, though they never understood exactly what they were, I'll come back to that later, but they understood that there were a lot of interesting symmetries in general relativity. And then another one is so-called soft theorems in quantum field theory. And a soft theorem, so there's a different language here for the same kind of structures. And a soft theorem is a statement of the following form. Let's imagine we have here a scattering of 4 particles, and one of them is a photon or a graviton. And then we take a limit where that one gets soft. That is, its momentum goes to 0. Well, it turns out that there's a universal formula which is applicable to any theory with a photon or a graviton. You don't need the Lagrangian, you don't know anything. You don't need to know anything. You don't need to know the higher derivative corrections or anything. And you can show that in the limit where you take this 4-particle scattering amplitude soft, and by the hashed lines here, I mean, I'm writing a Feynman diagram here representing the scattering, and the hashed line means, blob means the sum of all the Feynman diagrams, that it's equal to the same scattering amplitude without the external graviton times some universal function A of the momenta and polarizations of these particles over here. And then the third corner of the triangle, which is experiment, not theory, this is related to the so-called gravitational memory effect. And I want to emphasize that what I'm talking about here is not new physics. It's not a new proposal for what the microscopic laws of physics are. Whether it's loop gravity or string theory or M theory or something else we haven't yet discovered. It's a new way of new insights into the structure of the laws of physics and the limits in which we already understand them, namely long distances. And but we're understanding it in a new way, and that is it's becoming clear that is going to strongly constrain the consistency of how we march on from the infrared that we can measure into the ultraviolet, where we know very little. And putting these three things, when you can bring together different branches of physics, it's very powerful. And it's led to a lot of new insights into the low energy structure of gravity, of gauge theory, and it's relevant to the black hole information problem. That's the soft hair program. And it's also, there's been a number of experimental predictions based on this, and it's related to also the holographic principle. So obviously I won't get to all of that, but let me start. So what are the symmetries of general relativity? Well, one answer to that question is general covariance. But, that's not such an interesting symmetry, because if you have a diffeomorphism, which, well, I don't mean to say general covariance isn't interesting, but it's not the kind of symmetry I want to talk about, because if you have a diffeomorphism which vanishes near the boundary, it doesn't do anything either to the quantum state, to the classical field configuration. It's really just a redundancy of description. And in fact, we can describe general relativity using, say, Reggie calculus, and in loop gravity, the symmetries are different than in so these local symmetries than in ordinary formulation of Einstein gravity. And so these are redundancies of descriptions, and they don't lead to conservation laws or experimental predictions in general. And now, so for example, in special relativity, the Poincare symmetries all lead to conserved charges such as energy, momentum, and angular momentum. Energy conservation follows from time translation invariance via Nether's theorem. So in 1962, Bondi, Vanderburg, Mesner, and Sachs asked the question, how do Poincare symmetries, what are the symmetries of general relativity? How do Poincare symmetries and charges appear? And the answer was a huge surprise. So the key ideas was, first of all, the notion of an asymptotically flat spacetime, which can become very technical, and there are different ways of defining it. But roughly speaking, it's a statement that that the spacetime is like Minkowski space near past and future null infinity. So I'm assuming here you've seen a Penrose diagram. Penrose diagrams are pictures of spacetimes in which light rays go at 45 degrees. And there's past null infinity called scry minus, where light rays come from. There's future null infinity, where light rays go to. And then there's spatial infinity and past and future time-like infinity. This is a picture of Minkowski space. So an asymptotic symmetry is a diffeomorphism which preserves some boundary conditions. And again, it's very tricky how you choose these boundary conditions. And we still don't know exactly how to choose them. Mostly people have gotten it wrong, and then corrected it, then it had to be corrected again. And I don't think we're at the end of that process. I don't know what the quote unquote right boundary conditions are. And there's even a question of what is the principle that would determine what the right boundary conditions are. Anyway, they took some that seemed natural to them, and they looked at the space of coordinate transformations preserving the boundary conditions modulo trivial coordinate transformations. Those are the ones that do nothing to the data at infinity. And the idea here is that the physical data of a spacetime is, you know, the vol tensor, it's the flux of gravity waves through past or future null infinity. And so if you do some diffeomorphism in the middle, that's not affected. And they were fully expecting to get the Poincare group out of this. Obviously, in some long distance limit, general relativity should reduce to special relativity. No, they didn't. They got an infinite dimensional group called the BMS group. Now, but you know, recently by the Belgian group, Barnick and Troussard, it's been realized that that their boundary conditions were too strong, but and there's more, but we'll come back to that later. So it includes the Poincare group, but there's more. And the more are translations. So just ordinary time translations move our motion on Scribe plus, which moves every point on this sphere at Scribe plus, which we call the celestial sphere, at the same rate. But that's actually not to say that every point on a sphere out at infinity. First of all, in a general asymptotically flat spacetime, there is no preferred sphere at infinity. It's not meaningful to say you take a sphere, you go up to null infinity, and you go at the same rate at every angle, so you get a round sphere. This is not a meaningful statement. And so you can't tie together the structure. General relativity doesn't allow you to tie together the structure at the different points of the sphere. And so there's something called super translations, and it's a symmetry where you act at different points with translate them by different amounts. So if you had, say, a graviton coming out at the North Pole and the South Pole at the same time, you could do a super translation in which, you know, the one comes out at the South Pole 50 years earlier, and the one comes out at the North Pole 100 years later. That's a diffeomorphism, but it's a physically inequivalent situation. We could construct a measuring device which would distinguish between these two possibilities. So we can measure things that are not related by diffeomorphisms, that are not diffeomorphism invariant. Sorry, like we can measure the momentum of something, but you could do a boost and bring it to rest. So, and that's a diffeomorphism. But there are much more subtle things, and this is an example of one of them, of two different classical field configurations which are related by diffeomorphism, but we should not regard them as physically equivalent. And there's a similar group on Scri minus. Now, it was widely, so this bothered BMS, and it was widely held that these groups acted on Scri plus and Scri minus, but you couldn't relate them in any way. In other words, you couldn't make a statement that you had a symmetry of gravitational scattering. So that if you, in other words, if we have some incoming configuration that scatters to some outgoing configuration, if we translate it, the incoming configuration, it should scatter to the translation of the outgoing configuration. In other words, if we do the same experiment on Earth, and then we do it again on Mars, we should be able to predict the answer of the second one from the first one, because translations are symmetry. But we'd like to do this with the whole group, but that was thought to be impossible. And so many efforts were made to kind of kill this BMS symmetry by some kind of boundary condition at spatial infinity, but all of those had problems. And part of it was that there was confusion, which I won't go into, but about what structure exactly, what sort of regularity we should impose at spatial infinity, which wasn't really cleared up until, I mean, other people understood it in a way, but it wasn't really cleared up until, the work of Christodoulou and Kleinerman. So what we did, I guess, 7 years ago, is to show that, in fact, there is a combination of incoming BMS and outgoing BMS, which is a symmetry of gravitational scattering. In other words, if you do a BMS transformation on the incoming data, where you translate by an arbitrary function on the celestial sphere, and then you do the antipodal thing on the outgoing data, that maps one solution to another solution. And in the language, in sort of the quantum language of the S matrix, there's an operator B, which generates the infinitesimal supertranslations, and it commutes with the S matrix, just like the charge operator or the energy operator commutes with the S matrix. But those are just some finite number of things. Here we have an infinite number of operators, which I've called B, which commute with the S matrix. They have conservation laws associated with them. We'll see that the memory effect is the measurement of one of those conservation laws. And these are true symmetries of GR. They have physical consequences, which LIGO and the pulsar timing array and other experiments are trying to verify. So there's symmetries and conservation laws in the same sense that energy and charge conservation are symmetries and conservation laws. Not true of all of BMS. That, you have to have this antipodal matching. And you can think of this as energy conservation at every angle. It's not just that the total energy equals incoming energy equals the total outgoing energy. It's true that the energy coming in from the South Pole, flux integrated over all advanced time, is equal to the integral of the retarded energy flux at the North Pole, when you're very careful about the fact that the energy contains a total derivative term, which is linear in the fluctuation of the gravitational field, which doesn't contribute to the total bonding mass. Okay, another way to derive this, but from just matching at infinity, antipodal matching of the so-called bonding mass aspect. But I think I won't go into that. Wait a second. Oh, I dropped a, I'm sorry. Oh, okay, yeah. Okay, now I'm turning to what seems like a completely different topic, but it's the same topic I was talking GR language, now I'm going to talk particle physics language. So in 1965, 3 years after BMS, Weinberg proved something called the soft graviton theorem, which applies to any theory of gravity and is an exact statement about the quantum theory. Just have to assume the theory exists and is diffeomorphism invariant. So this is a soft theorem. So you have some scattering amplitude. You let the charge go to 0, and you get the same scattering amplitude without the insertion with one less particle, one less graviton, times this weird factor, which involves a sum over all the momenta of the incoming and outgoing particles, the polarization of the graviton, and the momentum Q of the graviton. And there's a pole in Q. You might think you get something finite, but in fact, it diverges in this limit. That's related to the famous infrared divergence problem in quantum field theory. And then there's a subleading term. Now, one can show that so the BMS supertranslations act as a symmetry, and symmetries have what's called ward identities. That is, we have this operator B this is 0, and now let's take its matrix element in any state. And okay, it's a bunch of algebra, but you just take the matrix element of this relation, which is true for any scattering amplitudes, and it turns exactly into BMS supertranslation symmetry. So these are just completely mathematically equivalent statements. BMS, antipodal BMS symmetry of the type I just described, and the soft graviton theorem are the same mathematical statement. You just have to work out the details of going from asymptotic data on Scribe Plus to gravitational plane waves and so on in momentum space, and they turn into one another. Now, one of the consequences of this is that the vacuum in general relativity is infinitely degenerate. And one way of saying this, and this was something which confused BMS, that G mu nu is eta mu. It's not preserved. It's preserved by the Poincare group, but not by super translations. And if you do a BMS transformation, you change the angular momentum of the vacuum. So there isn't a unique vacuum in general relativity. It's characterized by, among other things, its angular momentum. There's an infinite vacuum degeneracy. And at the quantum level, we can understand this as a statement that if you add a soft graviton, which by definition has 0 energy, you don't change the energy of the vacuum. To create a soft graviton, you don't change the energy, but you add 1 unit of angular momentum. So it must be an orthogonal state. It's a new vacuum. And we'll see that these vacuums can make transitions into one another, and that's what's being measured in the memory effect. And the words that would be used in particle physics is that supertranslation symmetry is spontaneously broken. So it's interesting that these essentially equivalent discoveries were made 3 years apart. All right, so now let me go to the third corner of this triangle, the gravitational memory effect. What is the gravitational memory effect? Well, suppose we have 2 inertial detectors, nearby inertial detectors, and then a gravity wave comes by. These could be the mirrors at LIGO. Well, they're not let's imagine they were on tracks instead of on pendula, so that they were inertial, or they were pucks floating. I don't know. Okay, they're not in the approximation where we can think of them as inertial. This could be LIGO. Gravity wave comes by, their distance oscillates, but then there's a DC offset. They don't go back to where they came from. How do we understand this? Well, we can understand this. Here's the equations here for those of you who have seen this before. This is the asymptotic form of the metric. This is the round metric on the 2-sphere. This first line is the flat metric. And then there's deviations from the flat metric if a gravitational wave is coming by. And interestingly, these deviations, the metric can be flat to this order, is flat to this order, if and only if this function, CZZ, so Z and Z bar are coordinates on the celestial sphere. For a propagating gravitational wave, C will have some time dependence, but I'm doing an expansion in R here. So by definition, C is the subleading component. This has an R squared, is a subleading component, so it doesn't have an R in it. And this is flat to the appropriate order if and only if C is some second derivative of some function C of ZZ bar. And now if we write down the equation of geodesic deviation and we solve it, we find that the shift between these two detectors is given by this formula, which is what one tries to remember. It's the change in CZZ. But the change in CZZ can only be of this form. And it turns out that this F here, which it's a function of this C, or it's equal to F, is precisely a BMS transformation, a BMS supertranslation. So we can think of this gravitational, this gravitational wave flux induces a BMS transformation on the vacuum. It moves the vacuum down here to another vacuum, which is related by BMS symmetry. Gravitational waves can be thought of as domain walls, or any wave which goes to infinity can be thought of as a domain wall, which gives you a transition from one vacuum to another vacuum. And this can all be made mathematically very precise. There's a formula for what the BMS transformation is as a function of the stress energy of the gravity wave, or it could be electromagnetic wave, also will do this, that goes through infinity. And this, it's hopeful, will be measured rather soon. And I think it's a really interesting measurement because it's a qualitative prediction of the Einstein equations that has not been experimentally verified. Now, I can't resist putting this slide on. Here's Weinberg's formula for the soft graviton theorem that he wrote down in 1965. And here's the formula of Brzezinski and Thorne from 1987. Weinberg was scattering elementary particles. Brzezinski and Thorne were scattering black holes and neutron stars. But this formula, particle theorists like to work in momentum space. Relativists like to work in position space. But you can go to one from another, doing a Fourier transform. It's very easy to see, just glancing at these formulas, that this is a change. Here there's a pole. The Fourier transform of a pole is a step function. So these are just exactly the same formula. But they sat there for decades before it was understood that this was the same thing, and that the soft theorem, the Weinberg soft theorem, which is equivalent, which is the word identity of the BMS symmetry, is the Fourier transform of the gravitational memory formula. So they're all related in a very simple and direct way. And it's wonderful having this tied in, because now it's not just abstract theory, we can hope to measure it. So there's a triangle, the memory effect, the symmetries, the soft graviton theorem. And now I want to say that this is just what these triangles reverberate through physics. There's actually, now we've discovered a whole tower of graviton theorems, soft graviton theorems. They also exist in gauge theory and in QED. There's similar triangles there, and there's all kinds of struggles triangles that we've been struggling with to understand, and some that we've already completely understood that describe new things about the laws of physics that we have already been experimentally verified. So now let me come back to the point which I've alluded to several times. What are the fundamental symmetries of the standard model of physics and general relativity? So the laws of physics that we are sure are correct. So I want to consider this question in the asymptotically flat approximation. So I'm going to ignore the cosmological constant. Interesting to try to include the cosmological constant, but there's a well-posed problem, interesting problem, that makes an approximation which is good for almost every experiment we would do, in which the cosmological constant vanishes and we can study asymptotically flat spacetime. So we're going to consider that. Diffeomorphisms, as I said before, are mostly trivial. The non-trivial includes, as I've just described, this antipodal subgroup of the BMS group acting on the future and the BMS group acting on the past. But we know for sure that there are more. And we know it from many different points of view. The BMS boundary conditions were both too strong and too weak. They were too strong. They eliminated something that Barnick and Troussard talked about, the so-called the conformal symmetry acting on the sphere at infinity, which there has, again, there's a diagonal subgroup of it. And again, there's been a soft theorem. It's been proven to be a symmetry by of the scattering problem with the soft theorem. But there's even more than that. There's this, it's a subleading soft theorem. There's a sub-subleading soft theorem. In fact, there's a whole infinite power of these symmetries, but they haven't been organized. We don't know what they all are. And there's not only there isn't even a conjecture on the table for what they all are. And this is a basic question about nature, which all the experiments have already been done that would help us answer this question. And it's a job for the theorists, and we haven't done our job. And we've had a long time to do it in. Okay, now, one of the things, but it's not a simple problem, which of course is fun. There's a lot of possible formalisms to address this question. And you could use the Hamiltonian formalism. You could look for charges that commute with the Hamiltonian. You could use the covariant phase space formalism, the S matrix, Lagrangian. You could describe everything in terms of soft theorems. You could look for try to find boundary conditions at infinity, including antipodal matching, and do an asymptotic analysis. They should all work, but it's a hard problem, and it's important to find the simplest approach. And one thing that is looking very simple now is something called, which exploits some of the new symmetries that we've discovered to repackage things in a way that transforms nicely under the symmetries, is what I call generalized currents on the celestial sphere. And we'll also see that this approach sidesteps. I mean, they're all equivalent, but it sidesteps having to make a gauge choice or a statement about boundary conditions. I'm going to be talking now about a recent paper, I guess in March, with Alfredo Guevara, Mina Himwich, and Monica Pate, and also a paper I wrote last week. So what's the basic idea? So the basic idea is here we have an S matrix in Minkowski's. Here we have an S matrix scattering amplitude in Minkowski space. We send in a bunch of red stuff, it interacts, we get out a bunch of purple stuff. And the first step here is we want to rewrite this as, and this is really just a matter of a change of variables, albeit a complicated one, in which we rewrite this as a kind of correlation function on the celestial sphere. In other words, the sphere that lives at null infinity. And for every incoming particle, we associate one of these red things. For outgoing particles, we associate a purple thing. And we think of these as operator insertions in a field theory, a conformal field theory, which lives on the sphere at the celestial sphere at infinity. And they have various labels, like their color labels, whether they're in or out. We would label them by their charge, we could label them by their energy, but there's a better thing to do. And so this is, at first step, this is just a rewriting, but it's a suggestive rewriting. Now, 99.99% of work on scattering in Minkowski space works in momentum eigenstates. But there's another basis because of this has a conformal symmetry acting on it. What do I mean by that? Well, the Lorentz group in 3+1 dimensions is SL2C, which is also the global conformal group. It doesn't map the sphere at infinity to itself, doesn't map the metric to itself. It does a global conformal transformation on it. And in fact, one of the things that we learned that the superrotations that Barnick and Tressart talked about, actually there's a subleading soft theorem, and they also are tied past and future, which is why I'm able to write one sphere rather than have one for the past and one for the future. This thing actually has the symmetry properties of the correlation function of a 2D conformal field theory. And 2D conformal field theories are perhaps the objects in physics, which two-dimensional conformal field theories are perhaps the objects in physics which have been studied in the most mathematical depth, and the objects about which there's the most all kinds of theorems and relations and so on. And so now we're in the fortunate position that all these symmetries that applied to two-dimensional conformal field theories, which are being studied for 40 years, we can now use those tools to study quantum gravity in 4 dimensions. There are experiments that measure 2D, 2D conformal field theories can be realized in the lab, but it also applies to this other stuff, which is a very nice situation. Now, that means that we're characterizing the scattering state not by their energy, but by their boost weight. So we write them as eigenstates of the boost conformal killing vector, not the time translation. And now the price you pay for doing this, here translations act in a simple way. Here they act in a funny way. They transform an operator from one boost weight to an operator with a shifted boost weight. And that greatly constrains what this correlation function can be. Okay, and it's also related to, let me just skip this because I'm running out of time. Well, why is this interesting to do this? Besides what I just said about, I already said this one, we can use the techniques of two-dimensional conformal field theory. But there's, of course, another reason here, which is that there's something called the ADS-CFT correspondence, in which, for example, a theory of quantum gravity, and this can be made mathematically very precise in string theory, a theory of quantum gravity in three-dimensional anti-de Sitter space can be rewritten as a two-dimensional conformal field theory which lives on its boundary. And this was sort of shown from some first principles in string theory, but even before that, Brown and Hedneau had gotten a long way towards this structure, yet just using symmetries, a bottom-up approach, just using the symmetries of quantum gravity and anti-de Sitter space. And what we're doing now is more akin to the spirit of what Brown and Hedneau did. We're just using a symmetry analysis, though I think we could learn a lot. That's that's a bottom-up approach. I think we could learn a lot if we could construct an explicit example of this structure with a top-down approach. So in general, we think the principle of holography, that quantum gravity in a bulk spacetime can be written as a theory without gravity on its boundary. We'd like to generalize that to flat space. And the first step in doing that is to understand what the symmetries are, which is what we have just been making some progress on, because both the bulk theory and the boundary theory have to have the same sets of symmetries. So another motivation for this is to understand how we generalize holography to flat space from anti-de Sitter space. Okay, so now let me describe what does it mean to represent a four-dimensional symmetry as a current on the celestial sphere. Well, here again, I've written the metric. This is the first three terms are the flat metrics. This U is the retarded time coordinate, R is the radius, this gamma is the round metric on the two sphere, and Z bar are the coordinates on the celestial, we call the celestial sphere. And then these are, in general, non-flat terms. And the derivative of these terms are called the bonding nus. They are they measure the gravitational radiation, which is going through null infinity. So we can form an integral, something I call the super translation current. And we take the super translation current, but we take the bonding nus, we take its divergence. And this is, I'm just using the constraint equations of general relativity, but in a way that may look unfamiliar. And I make this weird combination where I integrate this over a line along future null infinity, along retarded time along future null infinity, and I subtract from it the same thing integrated over past null infinity. And then you can use the constraints to show that, so what's left depends only on the coordinate on the celestial sphere, which I've drawn here, that this is a conserved current. And so if I consider a scattering amplitude in which, in addition to every other particles, I scatter one of these zero modes of the bonding nus, and then I integrate it around a contour in the celestial sphere. So I'm really rewriting everything in a different language, but it's just classical general relativity I'm doing here. However, importantly, the soft theorem tells us that this actually lifts to an exact quantum statement. So I take this thing and I integrate it and I weight it by an arbitrary holomorphic function, f of z. What I get is, because it's holomorphic, this thing has poles at the operator insertion, and I get it looks like a conserved current in a two-dimensional conformal field theory. And I can rewrite it as a sum of contributions at the poles, which appear at the operator. So, and to go from here to here, you just use the asymptotic constraint equations of general relativity. That's all it is, but written in a very unfamiliar form. In a form which looks unfamiliar to most GR treatments, but in a form which anybody who studied two-dimensional conformal field theory would say, oh yeah, I know that formula. And so that's it. And this gives a super translation. You can see it super translates the operator insertion 5 by an amount proportional to whatever this function takes at 5. So I can do arbitrary translations of these 6 different operators using different choices of this function. And if I choose it to be a constant, I'm just doing a global translation. So there is a way to think of, the lesson here is that symmetries of general relativity can be understood as ward identities of a two-dimensional conformal field theory of a type that's very conventional in that framework. And this turns out to be pretty mathematically powerful, and there are more currents. So you can classify, well, we classified an infinite tower of currents. And I want to say that I don't really understand this, but Newman and Penrose had a similar tower of conserved currents involving higher and higher, back in the 60s, higher and higher powers in 1 over r and higher angular momentum. It's a similar kind of structure here. I don't know exactly the relation. So these currents are labeled, we can think roughly speaking as this K and L is representing the boost weight of these currents, and this as relating their in angular momentum multiplets, and this labels their angular momentum. And this is and we managed to compute their algebra. And K equals 1 is the super translations. K equals 0 is the so-called super rotations and super boosts. And then that continues to a whole infinite tower. Now, various people had talked about the existence of this infinite tower because there's infinite towers of soft theorems, and Barnick and Troussard talked about, well, some of these symmetries don't seem to close and so on. So we got a complete closed algebra of conserved symmetries. This is the algebra, this is the symmetry group. You can check that this is translation invariant, and that this complicated formula obeys the Jacobi identity. And the mode numbers here are the modes under the global conformal group of the celestial two-sphere. Okay, now each current has an observable memory effect. The first one is the standard memory effect. And then the second one, which we wrote about a few years ago, related to super rotations, is called spin memory. And it's related to if you have like two things which are rotating around in opposite directions. Like actually we were hoping that the protons going in opposite directions at the LHC or something would be able to measure it, but it doesn't seem quite. They get a relative time lapse. They get out of sync, and then there are going to be more effects at every order. And there's an algorithmic way to compute what these effects are. Now, this looks pretty complicated, but now, and also, I haven't talked about gauge theory and QED here, but it turns out that there are similar formulas, which we also computed, for the symmetry groups of gauge theory and of gauge theory, and also gauge theory plus gravity at the same time. Then I realized there's this weird redefinition. This should be +4. I don't know what happened to that. Where you reorganize these generators, and and all of a sudden it becomes dramatically simpler. And not only that, it becomes a symmetry algebra, which Bacchus wrote down in 1987. It's probably the best known symmetry algebra. It's a higher spin symmetry algebra. It comes up in various integrable systems in 2 dimensions. It's the simplest and most discussed beyond the Versaro algebra, which is just, there's more generators here. In fact, if we said P equals to 2 and Q equals to 2, you have a closed subgroup here, which is just the Versaro algebra. So this generalizes the Versaro algebra. And so it's very nice to see this complicated looking formula. So we didn't set out to find W1 plus infinity. It's kind of the nicest infinite dimensional algebra. We found something which looked more complicated, and then we found a transformation which turned it into this W algebra. So this W algebra is a symmetry of scattering of quantum gravity in 4 dimensions at tree level. So really here, there's corrections to some of these formulas here. And there's a similar statement for gauge theory. And there's been a lot of discussion of these W algebras. Now, these are more technical comments, but I think the one thing I want to say is there's a very interesting, so it turns out if you try to realize this algebra, which we derived at tree level in a quantum system, it gets deformed. And there's a unique, it's very hard to find the deformation. These people and other groups, Pope, Romans, and Shen, in the early 90s, spent 2 or 3 years finding this deformation of W1 plus infinity, which is called capital W1 plus infinity. And there's a unique 1-parameter family of deformations that occurs when you quantize the theory. And so the hope is that something similar will happen in asymptotically flat 4D quantum gravity, and that this will provide an organizing principle for gravitational scattering and their symmetries in 4 dimensions. This part is, I mean, up till this slide, everything was this is all speculative, but it's certainly an interesting thing to think about. And it's all rather new. Okay, so in conclusion, gravitational scattering is a rich problem, both theoretically and experimentally. There are interesting experiments that we can do. And putting together asymptotic, the GR analysis, the particle physics analysis with experiments, it's leading to new insights. And it's a wide open subject with still a lot that we haven't understood. So I guess that's an hour, and I will stop there.
All right, thanks a lot, Andy. So there were already 2 questions in the chat. So maybe I read them. So the first one was asking, so does the equivalence between the soft theorem and the BMS symmetry indicate some holographic nature?
Well, okay, so yes. I mean, it doesn't prove it, but I think it's very strong evidence. So not the BMS itself, but the extended BMS. So we use the soft theorem told us about supertranslate. The soft theorem, the leading soft graviton theorem, which talks that it's a symmetry where you have angle-dependent translations on scri plus tied to the similar things on scri minus. That really didn't point to holography. What pointed to holography, and indeed suggested, this is far from the only suggestion about how we should think about holography in flat space rather than anti-de Sitter space. I mean, by the way, the first statement of the holographic principle is really the Bekenstein Hawking area entropy formula, which says that the number of degrees of freedom of a black hole grows like the surface of the black hole, not the volume. So that suggests that there's some way of thinking about it as something living on the surface. You know, the holographic plate lives on the surface of the black hole. But what did so what these people, de Boer and Solodukhin, said way back in, I think, 2001, they said, let's take Minkowski space and let's think of it as kind of a non-compact, and we can slice it so that these things are hyperbolic planes, constant negative curvature planes, which is Euclidean anti-de Sitter space. This would be de Sitter space. So let's write slices like this. And then, we can think of tau, the thing which parameterizes these slices, as a non-compact, we can think of Minkowski space as a non-compact compactification over anti-de Sitter space. That's what they said. Let's think of Minkowski space this way. And the minute you see anti-de Sitter space, you think, aha, there should be a conformal field theory that lives at the boundary there. So they conjectured that without really any evidence. We had ways of proving that in, well, Brown and Hanaud proved it when you don't have the extra dimension. We don't really know how the extra dimension figures into it. And they also thought that there would be two spheres and that somehow the holographic picture would be a map from this sphere to that sphere. Then along comes, then somewhat later, was Barnick and Tressart, who also came to the, so these things that de Boer and Solodukhin were talking about were later called super rotations by Barnick and Tressart, and they came across them in another way. And they came across them by arguing that basically that BMS had, their boundary conditions were too restrictive and one should allow for a meromorphic point-like singularities. Then Cacciazzo and I proved a soft theorem using traditional particle theory type Feynman diagram methods that showed that this symmetry group was there, but that's what this lock and chain is, that the symmetry was a symmetry where you act on here and on here. And so now you have a symmetry of quantum gravity in flat space. Whatever the holographic dual is, it should have the same symmetries. And of course, we know what kind of things are acted on by the conformal group on the two sphere. They're conformal field theories. So it's kind of, you know, hitting us in the face that the holographic dual should be the conformal field theory. Now, I just want to say it's not a conjecture that you can rewrite. It's been proven that you could rewrite until you're blue in the face any scattering amplitude in quantum gravity in the standard plane wave basis. You could rewrite it, and there people have done things like this in the form so it looks like a correlation function of conformal field theory, and it will obey the symmetries. That's been proven. That is, you can go from the left to the right. You could do that. The question is whether it's useful, whether good things are going to come out of it, and even more, whether you could intrinsically define the right-hand side on its own right as a two-dimensional field theory. That has not been done. And if it had been done, that's what we did for ADS-CFT and string theory. We have a left and a right. They have separate definitions. And wherever we can compare them, they agree. Here we only have a left. we don't really expect to get the right for the real world, because if you know that, you know, in the string theory examples, we know everything all the way to the infinite UV. That's not the real world. We don't expect to know everything, or I don't expect that we're going to understand everything about the real world. But still, it would be really great to have some examples of toy models where you could get an intrinsic definition of whatever the exact theory was on the right, and have an independent definition and show that they agree. And of course, this recent stuff I told you about is that we should look for very special conformal field theories that not just have the conformal group, but they have this whole W algebra, which is a generalization of the infinite dimensional generalization of the conformal group. So yes, it suggests the symmetries are the foundation of holographic constructions, and we're understanding a lot about the symmetries, and it's pointing in this direction, and we don't know how far we can go.
Thanks for the detailed answer. And so maybe a last question. There was a question in the chat about whether this idea of celestial holography extends to asymptotically ADS spacetimes.
Whether it extends to asymptotically ADS spacetime. Well, I guess I would answer that by saying it's the same philosophy that was used. I mean, it's the same philosophy that was used in ADS spacetimes. The symmetry that you get tend to be, except in ADS3, the symmetries tend to be very simple. They're just the conformal group on the boundary. So the symmetries aren't as powerful a constraint as they are. There's so many symmetries here in this celestial holography, you wouldn't even think there was a theory that could have all those symmetries. It seems over-constrained. But we know, because we can construct examples, that they do exist. I would say it's the same philosophy, and I would say, I would kind of phrase it the other way around, that we suitably interpreted what had been done in ADS and extended it to flat space. I would say that's how it started.
All right, thanks a lot. And okay, I guess it's time for the break now.